So a little bit more historical perspective. I'm going to talk about nonlinear optics, and like communications and photonics, this came about with the birth of the laser, and which was celebrated 53 years ago. When I built this slide, it was the 50th anniversary of the invention of the laser, which was demonstrated by Mayman at Hughes Lab in California. And he did not win a Nobel Prize, which is a scandal, but Towns, Basov and Prokhorov shared their prize for fundamental work leading to constructions of lasers, in particular the maser. And this is Charlie Towns, who is still alive and well, and this is Jim Gordon, who died only last week, unfortunately. Both iconic stars of the 20th century science, both at Bell Labs. I didn't overlap with Jim Gordon, but he was sort of one of the grandfathers of Bell Labs who would show up, and he was just so highly regarded. He built the maser that won Charles Towns. He was the student. Maybe he should have won a Nobel Prize too, but they only give out 3. We then have Bloombergen and Schaulow. Arthur Schaulow was part of the team who invented the laser, win a Nobel Prize for their contributions to laser spectroscopy, which led to the field of nonlinear optics and this fascinating concept that one light beam can interact with another light beam. Bloombergen is still alive. Arthur Schaulow passed away about a decade ago. So these great scientists, they live for a long time. Isn't that interesting? Many of them. Okay, so what is nonlinear optics? What is nonlinear? Let's see if this works. Linear is the idea that we have a superposition. 1 + 1 is 2. Nonlinearity is the idea that we don't always have a superposition. Bit cheesy, but you understand nonlinearity is when things don't add up in a linear way. Okay? So nonlinearity is present in many different systems. Understanding nonlinear behaviour, understanding nonlinear interactions is critical to all sorts of real-world systems in finance, in banking, social sciences, biology, chemistry, atmospheric physics, hydrodynamic waves, solar state physics and optics. Waves, for example, are very interesting nonlinear systems. Rogue waves in oceans are a real challenge for the shipping industry, and they are now understood for the first time through an analogy with optical solitons. Tsunamis are soliton waves, so nonlinearity shows up everywhere. Now in photonics, the concept of nonlinearity is that photons will interact with each other. Okay? But not in a vacuum. They interact with each other via the medium. So 2 photons sailing through each other at the speed of light in a vacuum will not interact. Okay? They do not know afterwards. There's no evidence that they've sailed through the other light beam. However, in a medium, there is an interaction. And the interaction comes about indirectly because one photon modifies the medium at an atomic scale which affects the other photon. Okay? So photons will interact. One light beam will affect another light beam, and that's what nonlinear optics is all about. Okay, a very fascinating field of modern physics. So a good example of nonlinear optics is simply the fact that when you are kids and you took your magnifying glass outside, saw some ants, you probably attempted to burn the ants by focusing the light down. That's nonlinear optics. Okay? At an atomic scale, what's happening here is that the electromagnetic field, the light field, is actually interacting with the electron cloud. Okay? The electromagnetic field is distorting the electron cloud. So at high intensities, when you send a light beam through this material, the electromagnetic field distorts the atomic structure, the electron cloud, and that changes the properties of the material, and it manifests an increase in the refractive index. We're all familiar with the refractive index? Okay? So the light beam will change the refractive index, and that alone is the basis of these all-optical photonic interactions. Now, importantly, this interaction is almost instantaneous. Okay, femtoseconds. Now, femtoseconds is an interesting number because that sort of relates to the inverse of a petabit. Gives you a sort of hint at why we're interested in the nonlinearity. Because 1 femtosecond inverse is a petabit. So we're going to exploit this photon-photon interaction to do the switching and the logic at these incredible bit rates. Now, the way we're doing that is to use these chips. Now, where are they? Who's got them? What you look at in one of those is this circuit here. We're building highly nonlinear glass circuits. We're using these lithographic facilities that I talked about that will be in the new building that are part of the capabilities that are used in the microelectronics industry to create these photonic circuits. Chalcogenide is a glass, it's a nonlinear glass, it's a magic material. It's very, very, very nonlinear. That's why it's special. Photolithography just means printing. We have strong nonlinearity, the mode volume where the light is confined to these very, very small mode areas. And we build these circuits. And you can see fibre going in, fibre going out. You can see that these are all very compact and all of the action is happening on the chip. So we've had a huge amount of press, a lot of excitement. This is, I'll show this again later on. This is my team in the Catalyst, and if you have some time and if you're interested, I would suggest you Google ABC Catalyst and you put my name or Kudos and you'll find a great story that was produced a number of years ago by Paul Willis, and we're sitting in my lab here looking very professorial. Okay, I'm going to run out of time here, Chris. Let's see. So this is now part of the nano age. Okay, so we're going to now really look at what's happening. We are now in a very exciting era for modern physics in that we can process at the nanometer scale to create circuits and structures and rings at a micron scale. For the first time, we have the ability to manipulate materials with sub-nanometer precision to build incredibly complicated structures. You might have heard about metamaterials. Okay, this is an example. I had lunch and dinner with Zhang Zhang, who's Berkeley. He's so impressive. I mean, this guy is just so full of energy. A science paper, nature paper every month. He's the guy that's leading the world in building these metamaterials. And three-dimensional photonic circuits are even possible. And I guess the roadmap is pretty simple for photonics. I mean, we're kind of only at the beginning. We're going from less complicated to more complicated photonic circuits. So as we go up here, we get to more density or complexity. This is the Moore's law for photonics. And I guess I like to say that what we're doing here in Kudos is taking photonic circuits to the next level. And so in the next 15 minutes, I'm going to try and finish on time. We've got photonic circuits that now incorporate metamaterials. They incorporate photonic crystals. They're very high functionality, they're compact, they're energy efficient, they're incredibly fast. And I'm waiting for a question pretty soon. Okay. I mentioned photonic crystals, a little bit of physics. So our research heavily relies on periodic structures, photonic crystals. These are materials in which the refractive index varies on a length scale of about the wavelength of light. Perfectly periodic structures in 1, 2 or 3 dimensions. So gratings, diffraction gratings is a good example. Fibres based on photonic crystals, an excellent example. You heard about this from Professor Philip Russell and Tanya Munro, I believe. Circuits in 2D, waveguide circuits that guide light along these channels in micron scale. 3-dimensional photonic circuits. 3-dimensional. This is incredibly challenging. There has only recently been a breakthrough in the field where this has been convincingly reported, and annoyingly it was from the same fellow from Kyoto that I mentioned before who reported the Raman laser. He's demonstrated 3-dimensional circuits in silicon. And it's fascinating to note that photonic crystals appear in nature. In fact, 10 years ago when I started the program here, the photonic crystals that were appearing in nature were actually better than the photonic crystals that we were making. And often people would say, why do you bother with lithography? Why don't you just have a farm and rely on butterflies? Because look at these beautiful, exquisite structures that are micron scale. And why do they have structure? What's the point? Why do you see photonic crystals in nature like this? Hands up. It's cool. Why do you think it's... yes. Camouflage. It gives them the colouring. It's a diffraction gradient, essentially. It gives them the colours. That's not pigmentation. That's the photonic crystal. That's diffracting specific wavelengths. And somehow evolution has allowed these structures to grow. And again, 10 years ago, they were better than the structures that we made then. But now, of course, we've got nanometer precision, so we blow them out of the water. I was going to just throw a few slides on metamaterials, because this is another paradigm shift that's come along. And really the last 5 years, it's taken off. And our new program has a big focus on metamaterials. And it really is a paradigm shift. And the motivation is that essentially naturally occurring materials, including photonic crystals, because they are naturally occurring, are limited. In terms of they have a positive index of refraction, they have a moderate nonlinearity. We are limited by the diffraction limit, bandwidth limits. And so the question is, can we do better? And Feynman said, eloquently, there's plenty of room at the bottom. Sorry. So what really this is about is somehow the scale gap between natural crystals, which have angstrom atomic spacing, and the visible light to create artificial materials. These are materials that have, if you like, artificial atoms that have these absolutely unprecedented properties that don't appear in nature at all. And so they were first proposed by Sir John Pendry, but they've only been possible in the last few years. And the basic idea is to create a material that has artificial atoms. And the artificial atoms are these sub-wavelength, 100 nanometer scale metallic resonators. The physics is pretty rich, but essentially these are metallic rings. The light field induces a current in these metallic rings that's resonant, and it creates a magnetic field, a magnetic property that manifests in a magnetic permeability that is just not realizable in nature. And it can be negative, it can be positive. You can dial in the magnetic properties of this material. Okay? I like to think of this as an artificial atom. Okay? And so it's had huge impact on the field. And I'm not going to have time to talk about it. It's still very early on in this field, actually. Nobel Prizes will be won. Probably the most elegant concept is the idea of a perfect lens. The idea here, and you won't probably get this because you've not been introduced to dielectric permittivity and permeability, but these are the physical parameters that define the electric and magnetic properties of the materials. And in nature, you simply don't see negative permeability. You don't very rarely see negative permittivity, and you never see negative refractive index in nature. Okay? But here you can create with these artificial atoms materials that have a negative refractive index. I mean, that's just mind-blowing. What does it mean? Well, it does manifest, for example, in the fact that you can have the perfect lens. There's no diffraction limit in a perfect lens, it turns out. Huge impact in microscopy. Huge impact in lithography in the electronics industry, because now in electronics, the size of the transistor is limited by the resolution limit of the laser that's used to write them. If there's no resolution limit, I can go down another factor of 10. We're trying to build photonic circuits that incorporate metamaterials on them. And so we've got a very exciting program to incorporate these beautiful structures onto circuits, and structures that look like this. State-of-the-art nanolithography to create nanometer scale spiral structures that are tunable. We have enhanced nonlinear behavior. We can control the polarization. We've got sub-wavelength control. Really unprecedented properties. And at the same time, we're trying to build an invisibility cloak. Okay? So that's a hard problem. Turns out negative refraction allows you to bend light in the same way that refraction does, but you can bend light in a way that makes something appear invisible, completely invisible. It's of real interest to, guess who? The defence. It works reasonably well at microwave frequencies, because at microwave frequencies, the length scale, the wavelength is much longer, so these structures are much easier, but at optical wavelengths, It's really hard, and it hasn't been convincingly demonstrated. Was there a question up the back? Yes. Good question. And so it turns out that is a field, optics in metals is called plasmonics. So when you hear about people doing optics in metals, that field is called plasmonics. And what matters in plasmonics is the so-called plasma frequency of the metal. And it depends if it's copper, if it's gold, if it's silver. That dictates the plasma frequency, and that dictates the frequency that you want to build your metallic resonator at. But the metals that are used are traditional metals. Copper, gold, silver, platinum. They're interested in the plasma frequency, the frequency where the light and the electron are most strongly coupled. In these metals, you have a fascinating situation that you have a photon field that drags current. That's why it's called a plasmon field. And so, very interesting physics in that question that you asked there. So, I did allude to this. I think I've got about 10 minutes, Chris. You started late, so I'll keep going. Who wants me to keep going? Okay. What do I need to do, Anne? I need to do this. Anne says if I do that, I energise myself. The adrenaline somehow. So we talked about slow light. And I mentioned this earlier. Someone said, well, how slow can you slow light down? Well, this demonstration was just spectacular. Lena Howe, who is a MacArthur Fellow in the US and Harvard professor now, slowed light down to bicycle speed in an ultra-cold atomic gas. And it was picked up by the New York Times, and this corresponded to bicycle speed. And so the whole field said, wow, what are we going to do with it? What's the limitation? Can we do it at room temperature? Can we do it over a bandwidth that's compatible with the information that our real world relies on, which is gigabits and gigahertz and terahertz? What's possible? And so we've been asking that, and our approach has been, well, let me go back. Here they're using an ultra-cold atomic gas, and the point is that they freeze this gas to such a low temperature that there's an absorption resonance that's so incredibly narrow that the light essentially gets stored in the medium itself. It sits in the gas, but it's at nanokelvin. So we're trying to create photonic resonances, not atomic resonances, but photonic. And we're going to do it at room temperature, and we're going to build it out of a photonic crystal. And it turns out we can do this over gigahertz of bandwidth. All right? And this was a review in Nature a number of years ago with my former student, who's now a patent attorney. And there's nothing wrong with that. That was fine. So the basic idea is that we can slow light down in one of these photonic crystals. Now, you haven't had the tutorial lecture course on photonic crystals, so you have to sort of bear with me here. But the basic idea is straightforward. These are little mirrors that are roughly a wavelength apart. And at a certain frequency, the light is going to resonate and it's all going to be reflected back constructively. It's all going to be in phase. But a little bit away from that frequency, the light's going to make its way through, but it's still going to bounce off these little mirrors. Okay? And the light's basically doing what my laser pointer is doing. Rattling around inside the structure. And we can slow light down over broad bandwidth. And that's sort of the schematic. And along the way, it does broaden. Yes? It does only work over a specific number of frequencies. And what my group is famous for is pointing out, one of the many things that we're famous for, and is pointing out that it can be quite a broad range of frequencies. The early demonstration by Lena Howe was over like a kilohertz. We've done this over a terahertz. But it is essentially, it's a resonant effect. And so the nonlinearity, this is a bit too complicated, but the nonlinearity scales now with the slowdown factor squared. We can enhance the nonlinearity, and this has been allowed us to make chips that are incredibly compact. Now, this is the old chip, and this is the new chip. And what's interesting here, because we've got this slow light enhanced effect, the light is resonating in the medium, we're getting more path length, we're getting more nonlinearity, and I'll show you an animation in a minute that'll do that justice. We can make incredibly compact devices and very energy efficient devices. Now, this little sliver here is about 1 millimetre long, but all of the action is actually happening in 100 microns. So this has given us 3 orders of magnitude reduction in the footprint of our chips. It's put us into a regime where we can do incredibly high-speed logic processing much faster than electronics on micron scale. So this is what's happening. The light is slowing down, and when it slows down, it spatially compresses. And this is a bit more, because here we're actually generating signal idler photons for correlated pair generation. This is actually a slide about quantum information, but it shows you the slowing down. It shows you light travelling at the speed of light, slowing down as it gets spatially compressed. Intensity goes way up. Okay, that's where we get this big enhancement in nonlinearity. This animation shows us we can generate correlated photons, individual photons that are then going to be used. We separate them spectrally, and then we do quantum information processing. But that's a separate story. Okay, let's see how we're going. We've got... going to speed up here. Okay, so we've got slowing light down. We're now really in a world where we're making these beautiful photonic crystals, and we're going to exploit them for circuits. It's interesting to note, just this point, I started off earlier on making the point that electromagnetism spans across this entire frequency range. All of the pioneering experiments in this field, when something like photonic crystals or metamaterials comes along, the first demonstration is inevitably at microwave frequencies. And why is that? Longer wavelengths. And you can build a photonic crystal macroscopic, drill holes. But now we've got beautiful lithography. Look at this. There's a million pillars. Okay, this is the type of structure we'll make at the AIN. There's a lot of effort also in self-assembling structures, relying on chemistry. For those who do chemistry, interested in chemistry, photonics comes up in a big way because chemists are interested in self-assembly of colloids, where you can assemble these exquisite, three-dimensional structures in a beaker. This is one of our old samples, just to take you on a tour. You can see, look at this. This is only 100 microns by 100 microns. And as we go in, you kind of see, and the granularity is actually an imaging artifact. That's 100 microns. How many holes are there? There's maybe 200 by 250,000 holes that have been drilled into this, and it takes 15 minutes. That's sort of exquisite control, Then you've got three-dimensional structures. This is Yuri Vlasov at IBM now. This was self-assembled. Look at that, beautiful. The problem with self-assembled structures, who wants to have a stab at that? What's the problem with this approach for creating photonic circuits and photonic crystals? Yes. Not always perfect. You can see, this is almost perfect here, but then look at these defects. So, unfortunately, natural forces are not good enough, so this is so-called bottom-up approach, as opposed to top-down. So I'm going to end and just going to talk about really what my research group is doing concretely. So I've been leading this Kudos program now for 10 years, long time. Some say I could be ready to move on, but I'm not yet ready to move on. We're focused on the photonic chip. And my group really works in these two disciplines, nonlinear optics, and you know all about that, and I hope you're excited about that, and nanophotonics. And we're trying to build a revolutionary photonic circuit. You've got a few of our older versions today. And the three areas where my group is now focusing on, terabit per second. I should change that to 100 terabits, because terabits is now passé, We're talking about petabits. We're now generating for the first time on chips individual photons, single photons, qubits. I haven't got time to talk about that, but my group here has got an amazing program. We're generating individual photons, one by one by one. We can manipulate individual photons, and we can start to think about quantum information processing at the individual photon level. And my laureate fellowship, just to mention briefly, is interesting because for the first time we're starting to look at nonlinear optical phononics. What's phononics? Sound, quantized acoustic waves. So it turns out in these chips that you've got with you, that you've been looking at, we can optically excite phonons that are guided in these waveguides. And we have these incredibly interesting interactions between optics and sound on these circuits that yields some pretty exciting processing applications. So we've had big impact in these chalcogenide circuits. We've talked about that. We've been developing instruments. This is a technology that my group is trying to commercialize. This is a schematic of a complicated chip. It's got a laser, it's got gratings, it's got detectors, it's got a microprocessor. We've done some spectacular work on slow light. I'm going to show you a slide in a few minutes. In silicon photonic crystals, we're interested in slow light. And we also play around in optofluidics. And for those that don't get the details, if you're in science these days, if you want to impress the audience, you show lots of nature, because that's the big journal that everyone's chasing. Nature Photonics is one of the top journals, and it has an impact factor of 28 for the 3 people in the audience who know what that is. But these are big journals, and every time you put out a paper like this, you get in the media, and you get a call from all sorts of journalists, and it's very exciting. So the group has been very successful. We've had the media attention, as we've talked about, and when we do report one of these breakthrough results, this is a review story, we get picked up by the media. The media in Australia these days is much more sophisticated. They love good science. They used to just want to talk about astronomy, but now, nothing wrong with astronomy, but now they want to talk about I want to be careful. Now they are happy to talk about things that aren't astronomy. So we are frequently picked up, and even earlier this year, my colleagues, a big result, and my colleague here, Arthur Lowry, who was just awarded a laureate fellowship earlier this week from Monash, a big result that was reported at OFC in California, and it got picked up in the local media and got some attention. I see a hand up. Sorry?
How many scientists your group is
6. Don't be impressed. I mean, the guy I was talking to, this Yang Zhang from Berkeley, has probably 50. So, it's what we're chasing. And they're very hard. Not only is the science beautiful, but the writing has to be beautiful. You've got to be able to tell a story. You've got to be right at the frontier. My colleagues in the school have been routinely publishing in Nature. Our head of school, who's here, I think dominates Nature in the last few years, it turns out. So if you want to hear... But I think when you're discovering planets or looking at wobbles in planets, that somehow, they like that, don't they, Tim? It's sexy. Anyway, yes, a couple of questions. Would I be able to use that as a high-intensity laser? I mean, that's an interesting proposition. The answer to that is yes, but in my effort, we're not doing that. But remember, I alluded to this recent Nature paper by the Kyoto group of a Raman laser in silicon. The way they made the laser so compact is to actually resonate the light inside a cavity, which is essentially slowing the light down. And then they optically pumped it, and they got lasing emission in this incredibly compact silicon chip. So yes, lasing, the slow light is essentially like a cavity effect. So you can make a laser. Good question. Yes, you're first. That's very slow, though. Tectonic plate movement is very slow. Bad news, yeah. Well, no, that's the big issue. That's why there's so many of them. They build a lot of redundancy into these networks. And you wouldn't even know. They go down quite frequently. And often it's terrorism. Or it's often the US trying to prepare for an invasion. Okay, so when they went into... Is there something funny going on there? Settle down. It's worth noting, when they went into Iraq 10 years ago, the first thing they did is cut a whole bunch of the submarine communications links. The whole area lost internet. So the US, the Russians, they have submarines that can go underwater, they can tap, they can cut, they can do all sorts of things. Let me just wrap up and do a roller coaster ride here. This is a great experiment that my former student did, and it's generated such excitement because we observed green light coming out of this silicon chip. Bill was in the lab. Great story because it was a discovery. He didn't expect it. He was pumping this chip with 1.5 microns. He saw green light. He walked into my office with Chris Dell, my former fantastic postdoc, and said, we see green light. We see white light. It looked white. What's going on? And I said, maybe the slow light is enhancing the nonlinear effect so much that we're generating third harmonic generation. We're getting the 3 omega created by the nonlinearity. And they went back in the lab and it was perfectly green at an angle. Silicon's opaque. It's like brick in the visible. So this has been cited 140 times. That's a big deal in the field. Great breakthrough experiment, and there's been a whole body of work that followed that. We've had exciting work. My colleague Martin Desturkey and myself, for many years, were excited about gap solitons, waves that propagate slowly. Someone asked before why these slow pulses were spreading out. And that's a great question, because the problem with all of these slow night systems is the pulses were dispersing. And so we proposed to create a soliton wave. A soliton is a wave packet that propagates in a dispersive medium without changing shape. Tsunamis are soliton waves. They maintain their shape. And so we reported here a soliton called a gap soliton that propagated slowly. It was dispersionless, and that was nature physics. Okay, so look, the punchline is I want you to go away and forever remember me, remember Kudos. When you out there in your real world, hopefully we'll still be around. The Kudos is a centre doing nanophotonics. We've got a great group of people across Australia. We're vertically integrated. We're making these incredibly exquisite structures, at the scale of microns. Here's the Sydney Opera House. We've been hosting big conferences. We're putting the flag up internationally. In the media, we're working with companies. Our students have gone out there and they're doing amazing things. And the impact is in areas that you don't always imagine. It's not just about more bandwidth. If you look at our agenda these days and the types of people we talk to, of course the impact of communications, e-teaching, but we're working with the astronomers. We've got a joint program with the Australian Astronomical Observatory to create novel instrumentation. We're working with DSTO in Sydney in quantum information security. So I'm going to end there. This is the team down at Mara Morang, and I'm happy to take any questions until Chris tells us we can't have any more discussion. Thanks very much.